the invertible matrix theorem. So if we have a square n by n matrix, then the following statements are equivalent, meaning that each statement, they're all either true or they're all false. Or you could say if one of them is true, that means all of them are true. Or if one of them is false, that means all of them are false. So the first one is A is invertible. If A is invertible, that means A inverse exists. So if A is invertible, that means A is row equivalent to the identity matrix of the same size, right? So in our previous video, we saw that if we row reduced A augmented with I and we got I on the left, that meant that we got an inverse, and that inverse was the matrix on the right. So if A is invertible, then A is row equivalent to I. Another thing we figured out is if A is invertible, then the determinant of A cannot be 0. Remember, we had to divide by the determinant to get the inverse of a 2 by 2 matrix, right? So this is true for all matrices that are n by n. If you get a determinant that's equal to 0, then you can't get an inverse. So here, the determinant of A is not 0 if it's invertible, and vice versa. There's a lot of these, so get ready. So A has n pivot positions. If A is invertible, it's row equivalent to the identity matrix that's n by n. That means there's a pivot position in every row and every column. Right? We could say that too. A has a pivot position in every row and every column. Okay, well that means that the homogeneous system, if I set up the system AX equals 0 and I augment with 0, then if A reduces to the identity and I've got a pivot in every row and column, then that means this has only the trivial solution, right? We can't get free variables. This has only the trivial solution. Well, that also means that if I have AX equals B, this is consistent for all B in Rn, right? Because if A reduces the identity, then I can't get a free variable, right? I can't get a no solution. So let's say this too, it's consistent and the solution is unique. There's no free variable, there's no infinitely many solutions. This has a unique solution for all B. And because I have a solution for all B, and you could also say, since I have a pivot in every row, I could say the columns of A span Rn. Right? The columns of A span Rn if Ax equals B is consistent for every vector in Rn. So if I span the columns of A, I can get every single vector in Rn with different linear combinations. All right, also, we're making a big list here. Because I have a leading one, a pivot entry in every column, then I could say the columns of A are linearly independent, right? And that comes from this as well, right? If ax equals 0 has only the trivial solution, then the columns of A are independent. Let's see, is there anything else? Oh, the transpose is also invertible. If it's square and it reduces the identity, then when you take the transpose, it's still going to reduce the identity and it's still going to be invertible. So that's a big list. And we actually can, later on when we learn more stuff about linear algebra, we can actually add to this list. If A is square and it reduces the identity, or it's invertible, then a bunch of stuff. We know all this right now, and we'll know more things later on.